All right, 4.2, we're looking at more historical numeration systems. The way that this is divided, right, between sections 1 and 2, is that section 1 had a lot of repetition of symbols, but not a lot of positional base value. The Chinese at the end did have a little bit, right, where we did things that are times 100, times 1,000. But what we're going to see in the next system is we're going to see things that are not in base 10 and that have positional values that are a little bit different than what you might expect. All right, so do you know, or do you think you might know, why we use base 10 for our number system? It's your fingers. There's 10 of them. So if you were like the cartoon characters, have you ever seen cartoon characters and really looked at how they're drawn? How many fingers and thumbs, and how do they have? Usually they have 4 on each. It's usually 8. It's usually a thumb. It's like this, right? If that's how God really made us, and we had 3 fingers and a thumb instead of 4 fingers and a thumb, we would probably use base 8. Does that make sense? Are you with me? So there are some reasons why other systems have been done the way that they are. So the first one we're going to look at in this section is the Babylonians. The Babylonians' numeration system only has 2 symbols. Yeah. You know it's going to be good when there's 2 symbols, right? The symbols aren't real hard. They're not hard to draw. It's a triangle that looks sort of upside down, if you will. And it's sort of an arrowhead-looking shape that opens to the left. These are their symbols. Now, for the sake of drawing purposes, when I draw them, I'm going to draw them empty. Because it's actually, I don't even usually draw that. I usually just draw the less than sign. So just FYI, when I sketch them, I'm going to sketch them in an abbreviated fashion. But the actual symbols look like they're filled in. Everybody good so far? 2 symbols. You might be thinking, well, how am I going to do this with 2 symbols? Well, they do repeat symbols that are less than 60. So if they wanted like 55, they do 5 of the 10s, so 5 arrowheads, and then they do 5 of the triangles. Okay, so if the number is less than 60, it's just repetition of symbols, just like the Egyptians used. But if the number is bigger than 60, they use a positional base system, and their base system is based on the number 60. Now, you see traces of Babylonian stuff in a couple of places in your everyday life where we do use, and at least do see, base 60. Where do you see it? Minutes and seconds on a clock, right? Where else? It's more math related, but it's used in degrees of a circle. You might say, well, that's not 60. You're right. It's 360. But it's connected to that same idea, all right? Our circle, our units are degrees on a circle. They did lack the number 0. So you may not have liked the traditional Chinese that had the zeros, or at least not their symbol for it. But lacking a 0 is going to cause us some problems. It's not going to cause us really problems, but it caused them problems. So I'm going to show you why that's a problem. None of your questions are going to have like issues with this per se, but there is a problem with not having a 0. Okay, are you ready to take a look at some? These are different. So here's the first ones. Go ahead and write those down because, again, I don't have a way to draw them for you very well. Yes, Tamara.
Math 5 is going to be multiple choice. Is it going to be multiple choice looking like those? Like
Yep.
you drew or from Google?
Well, it'll look like...
Will you be drawing it or will it be like numbers? Like not numbers, but like symbols already.
It will already have the symbols in there. So like, let's say that it starts with, this isn't a good example, but when we go over here, it gives you 3,280. It's going to give you 4 answer choices all drawn in symbol form, and you're going to pick which one it is.
Okay.
Does that make sense?
Yeah.
Okay.
I just wanted to know if it would look exactly like that or just it would resemble those.
They're very close. I've tried to draw them as accurately as I can anyway. I'm not an artist though, so it's definitely not a perfect match. They won't look white. These are looking white and on the black backdrop just because of the contrast I was looking for. They're drawn like that. They're darker, kind of like the first screen I did when I had the lighter backdrop. So, okay. So you should be asking yourself, where do I break place value? Right? I see triangles and I see arrowheads, and there's a bunch of them all together there. Where is the place value break? The answer to the where is the place value break is it breaks when a smaller number is in front of a larger one. Okay? So right now, if I sort of list again the numbers out, this right here, these are worth 10, right? So this is actually 20. Right, they're two 10s, and this is a 1. So right now, arrows in front of triangles, that's big in front of small, I don't break the place value. But then I come back over here and I see another 20. I have a bigger place value. That tells me that this breaks right here. A bigger symbol that comes after a smaller symbol breaks place value. And then I have a 2 over here. Okay, so everybody good with how we're making the decision on the drawing the vertical line and breaking it up? Okay, so let's talk about what it means by it being base 60 now. So on the right-hand side, it's pretty straightforward. I've got a 20, I've got a 2. This is the number 22. It's in the ones place for as much as we can know, right? Just like our system, we have a ones place, a tens place, a hundreds place. It's in the ones place. The problem over here is that this isn't the tens place because they don't have a base 10. They have base 60. So in base 10, if this number, this is a terrible example to use it with, but pretend with me for just a moment. If I had the number 21 in the tens place, it would be 21 tens. Right? Can you imagine dollar bills? I have 21 $10 bills. That's what that would mean. But it's not the tens place, it's the 60s place. So imagine having a bill that's worth $60. I have 21 60s. So their place system, I'm going to flip back, I'll come back to this slide though, I promise, has the ones place. It's written on the right-hand side, smallest, just like ours. And then it has the 60s place. Then it has 60 squared, and it has 60 cubed, and it would continue going up, just like ours does. Ones place, tens place, 100 is 10 squared, 1,000 is 10 cubed. It's powers of 10. They just use powers of 60. So we end up with 21 times 60 plus 22. And these sections, in particular this one, is really the first time you're going to really need your calculator on a regular basis because you're not going to want to multiply these. Maybe you don't need it per se, but you're going to want it. So some of our calculator use on the last 2 chapters has been minimal. It really hasn't been very much. It's going to be kind of significant when we get to chapter 4. All right, so what is 21 times 60 plus 22? Somebody multiply for me. Okay, say again, 1,282. That okay? I mean, it's not yet, but is it starting to sort of make sense? Okay. So take a look and just try for yourself for a minute. If you have a pencil, it'd probably be better than a pen, but try to put in where you think the place values are going to break here. And then we're going to check and see if you suspected the right places. Where do you think the place values break? Does everybody have them drawn in where you think they are? Yeah? Okay. So these are tens, and these are ones, and then I have tens next. So one of my place value breaks has to be here. These are tens. This is a 1, and then I've got another 10. So I have another place value break here. And then I have tens and ones, and there's nothing else. Okay, everybody good? All right, so what we're going to do is we're going to write the value of each of those, and then we'll look at what place value location it's in. So we'll start on the left because it doesn't really matter. I have 4 10s and 3 1s. What's that number? 43, right? 4 10s, 3 1s, I've got 43. In the middle, I have 2 10s and a 1, 21. And at the end, I have 1 10 and 1 1, that's 11. But I'm in base 60. So I have this 11 at the end. It's in the ones place, that's fine. So this is the ones place. This, however, I don't mean to draw it like it's a fraction. I don't want to write it that way. This one, the next one, the 21, is in the 60s place. So this 21 would be multiplied by 60 because it's in the 60s place. And the 43 is in the 60 squared place. So it will be multiplied by 60 squared. Okay, powers of 60 because it's base 60. And then your calculator gets to multiply everything for you, right? Told you we weren't going to want to multiply this out. 43 times 60 squared plus 21 times 60 plus 11. What's our total? What'd you get?
156,071.
You're right. Very good. 156,071. Okay. Got to move on. 3280. All right, this is going to be a little different. We haven't had to turn something into another number system where we had place values to be concerned with. At least not place values that weren't base 10, because that's what the Chinese had. It was base 10. This is base 60. So what does it mean? Well, it probably means to start with that we need to recognize what these values are. 1 and 60 is fine, but what is 60 squared? Don't everybody talk at once. 3,600. What's 60 cubed? I don't have this one written down. Oh, I do. I have it above. 216,000. And I could do 60 to the 4th and 60 to the 5th if I needed to, right? This is enough for what I need, at least at the moment. They're powers of 60. So here's how we do this. If I multiplied by powers of 60 to turn it from their system into ours, I'm going to do the reverse to go from our system into theirs. I'm going to divide it by powers of 60. So that's where we are. We're going to divide this by powers of 60. 3280. Looking at the numbers I listed at the top, what's the biggest number that will actually go into 3280? It's just 60, right? It gets too big when we get to 3600, agreed? So I will divide this by 60, and it's going to look like kind of like traditional division, but I'm going to end it, and I'm going to have a line on the left or on the right. And your calculator is going to do this for you. You're going to figure out how many whole number times 60 goes into 3,280. How many whole number times is it? 54? Is that what you said? Huh?
54.
It's 54. Okay. And then you're going to let your calculator multiply 54 times 60. What is 54 times 60? 3,240. And we line it up and we subtract. What is the subtraction going to give us here? What's the difference? Yep, 40. And then you're going to divide by the next place value down. Well, this isn't a very exciting one. We had 60 and now we have 1. But that's okay. We're going to write a 1 here. How many times will 1 go into 40? 40 times. 40 times 1 is 40. You will always have a 0 at the end. And your last division step will always be dividing by 1. Okay? And you're not done because these are not Babylonian numerals, are they? Nope. How do I write 54 in Babylonian? Five of the arrowheads and 4 triangles. And you'll see them stack some of these sometimes as well, just FYI. So stack them if you wish, much like the Egyptians did, where they kind of stack them once they exceed 3. I'll leave mine unstacked this time. And then I need the number 40. How do I get the number 40? 4 arrows. Oh, I'm out of space. Shift this over. It's almost down the space, but it's okay. 4 arrows. That's the Babylonian numeral that corresponds to 3,280. Let's do one more. 43,205. So what's the biggest number I need to divide by on this one? Yeah, I actually need to divide by 3,600 this time. Oops. All right, in your calculator, how many times will 3,600 go into 43,205? 12? 12 is right. 12 times 3,600 is, I don't have this written down, so somebody's going to tell me. 43,200. So when we subtract, what do we get? Just 5. And I know this is going to feel funny for right now, but we're going to divide by the next power down of 60, which is 60. And it's going to go in 0 times, and it's going to be 0 times 60 is 60, and it's going to sort of propel us into our last step of division by 1. We're going to do it here for consistency for something we need later on in section 4.4. That's really why we're doing it, okay? But then our last step is how many times does 1 go into 5? 5 times. 5 times 1's 5. Subtract, we have 0. And I'm about to have a problem. How do I write the number 12? An arrow and 2 triangles. That's the number 12. What's the problem? There's no way to show that I'm going to skip past the next one, is there? There's no way to write a 0 and to show the place values being held. We can skip a space for it, but how do you know that that space just represents 1 0? What if it were 2 zeros? That's not very good, right? That leads to some ambiguity. It leads to problems. It won't lead to problems for us because you're not going to be dealing with any that are going to create that. But I want you to see there are flaws and there's reasons that these things died out. Right? They did not survive, the test of time is because there's problems with them. How do I do the number 5? 5 triangles. So we can leave sort of a space in between them to at least represent that those 5 triangles are not supposed to be mushed in with the other 2 triangles. But I still have no way to represent the number 0 that's holding the place between. So you very legitimately could be given, not you, but given or see this number and think that it doesn't mean that I have 12 3600s. Maybe I just have 12 60s, right? Because I have no way to represent that I'm missing my 60s column. Yeah. Okay. Our last one's Mayans. The Mayans have some features that are similar to the Chinese. They write things vertically. And they have some features that are similar to the Babylonians in how they do place values. So their symbols, they do have a 0 though. That's a good news kind of feature. Their 0 actually looks like a shell. Or, I don't know, piece of bread. The number 1 is a dot. The number 5 is a horizontal line. It is written vertically like the Chinese. Dots are written on top of lines within the place value. They have a modified base 20 system. So they have a 1's place, they have a 20's place, and then they have 20 times 18. It doesn't go up to 20 squared right away. It's 20 times 18. And then 20 squared times 18, 20 cubed times 18, and so on. They do repeated symbols within the position like the Babylonians. Okay, so we're going to do some examples. Same thing. We're going to go from their system to ours and then our system to theirs. If you didn't quite get all this written down, just check the video out later. I'm sorry. I do want to make sure we get them finished. So these are our symbols. The first one is 4 dots over 1 line and then 4 dots over 2 lines. And then the second one has 2 dots, 3 lines, shell. 1 line, 1 dot, 1 line. So, much like we talked about with the Babylonians, we need to make sure we understand where the place values change. Place values always change around a 0. That's going to happen in our second example. But dots have to come above lines. So if you see a line with a dot underneath it, the place value had to change. There has to be a place value change here because there's a line above my yellow line and there's dots that are below it. Okay? We have 4 dots and a line. How much is 4 dots and a line? It's 9, right? Line's worth 5, dots are worth 1. That's 9. How about 4 dots and 2 lines? 14. But their place value system is powers of 20-ish. So they have, this is the ones place, and then they go up from here, and this is the 20s place. Then they would do 20 times 18. The 20 times 18 is actually equal to 360, and if you remember, the Mayans were the calendaring folk, right? And the 360 didn't come from what you might think of. It actually came from what they expected the days of the year to be, right? They were close. Ancient civilization, they're very close. 365 and a quarter, right? Ish. They suspected 360. That's why they really wanted their place value system to contain a 360 in it. Okay? So we're going to do just like we did with the Babylonians, and we're going to multiply. So this is 9 times 20, and it's 14 times 1, or just 14. If we add these together, we get 194. On the second one, changing place values, we're going to change it around the shell for sure. And then again, anytime there's a line over a dot. So I need one more down here like this. Okay, on the top, I have 3 lines, 2 dots. How many is that? That is 17. Shell is worth 0, so we have a 0 placeholder. That's very friendly, didn't have that a minute ago. Then we have a line, 5, and then we have dot line, 6. Place value works from bottom up. This is the ones place, the 20s place, and then I have 20 times 18, or you can write it as 360 if you wish, and then 20 squared times 18. So it's always powers of 20 above this, but always times 18. 20 cubed times 18, 20 to the 4th times 18. So we're going to multiply 7 times 20 squared times 18. I'm sorry, 17. I said 7, but I meant 17. Plus, now it's 0 times 20 times 18, so that's just 0. And then plus 5 times 20 and plus 6. The total this would give us is 122,506. All right, so we're going to finish up our last 2 examples. We're turning our number into their number. To start with, we have the number 208, and I'd like to list, kind of like I did on the last one, what our place values are. So there's the ones place and the 20s place. And then I have 20 times 18, which is 360. And then I have 20 times 18 times another 20, so that 360 multiplies by 20, which gives me 7,200. If I multiply by another 20, I get 144,000. And I think that's probably enough for the purposes of what we're going to work with. Obviously, you could keep multiplying by 20s and increase that value. So we're going to do the division just like we did with our Babylonians. So we're going to take that 208 and divide it by the biggest value that we have that's smaller than 208. And that number is actually the number 20. So we're going to start by dividing by 20. So 20 goes into 208 10 times. 10 times 20 is 200. Subtract it leaves me with 8. And then I do the number 1. So 1 goes into 8, of course, 8 times. multiply, get a 0 at the bottom. The difference, of course, right now is that I actually need to write out what does 10 look like and what does 8 look like. So 10 is 2 lines, and then 8 is 3 dots and a line. Okay? Our last one is 58,000. Well, let me square that in. It's 58,532. And again, the biggest value we need to look at is actually 7,200, and it will go into the 58,532. So if I take 58,532 and divide by 7,200, it goes in 8 times. 8 times 7,200 is 57,600. If I subtract that, I'm left with 932. And we'll go down the list. So we divided by 7,200. Now we're going to divide by 360. So 360 is going to go in 2 times. Right? And then 2 times 360 is 720. If I subtract, I'm left with 212. We'll divide by 20. It's going to go in 10 times. 10 times 20 is 200. Subtract, I'm left with 12. And I divide by the number 1. The number 1 goes in 12 times. 12 times 1 is 12. Remainder 0. So now I need to write the number that represents 8, 2, 10, 12. So the number 8 is 3 dots and a line. That's 8. The number 2 is 2 dots. The number 10 is 2 lines. And then number 12 is 2 dots and 2 lines. And what I want you to see is that there is a confusion here, right? If you were really starting with this numeral written the way that I've written it, even though there was a 0 in this system, and so it sort of fixed some of the problems, it doesn't fix everything. In particular, notice that right here, this has no guaranteed place value break. There is one, right? It should have been right here. It went from 2 to 10. But there's no way to guarantee that we can see that in how the numeral is represented. So in a very real sense, it looks like there's 8, 12, 12. Well, that would be 8 times 360 and 12 times 20 and 12 at the end. And that wasn't where we started. Again, it's not going to come up in any of your assignment kind of things, but I want you to be aware there is a flaw and there is a problem with this system.